So roughly, the question we ask now is how entangled is a quantum state? Given its Schmidt decomposition. So I have a state and I have it in the form of its Schmidt decomposition. Uh, how entangled it is. So we've seen that if the Schmidt number or the number of non-zero lambda i's is greater than 1, then the state is entangled. Intuitively speaking, uh, the Schmidt number itself captures how entangled the state is. So degree of entanglement in a state is the Schmidt number. And intuitively, it actually makes sense because if you look at it, the Schmidt number uh, helps us quantify the complexity of a state. So intuitively speaking, a product state in the sense a state in the form of just a tensor product, this is the simplest possible state in the sense it can be written just as a product of two states, one on system A and the other on system B. And the states which cannot be factored like that, we call them the entangled state. And the more the Schmidt number is there in a Schmidt kind of a decomposition, we say, well, the state is more complex. It is the furthest away from factoring that state. So now, why is the Schmidt number important? I'll give you an example to show you. For example, let's say I have a state of the form 0, 0, or I can also write it as 0 state on system A and 0 state on system B. Now this we know is a product state or an unentangled state. What about the state what about the state? Now if you look at it, I'll just write it again. If you look at it, it is hard to see it this way because it has got a bunch of terms with different coefficients, but as you can see, this is nothing but a tensor product a product state. So hence it's an unentangled state. It is a product state as a state on a system A tensored into a state on a system B. Though an expansion of this form, it was not easy to see that. That's why we need a Schmidt decomposition. So a Schmidt decomposition would convert this state into something like And in this case, since we have a product state, we can relabel these states as some, let's say, some funky vector uh, in this direction and another vector in this particular direction. So this state is nothing but this particular, where I have relabeled my quantum states. I'm just relabeling and denoting this particular state as this vector, and similarly for system B, I'm denoting this particular state, sorry, this is A, as this vector. So relabeling my bases and transforming this particular state as this guy, I see that this was nothing but a product state, and this indeed is actually the Schmidt decomposition of my initial state. So Schmidt decomposition, in other words, is a way of looking at the quantum state that tells you how many degrees of freedom the state has, and where by degrees of freedom I mean the Schmidt number. So Schmidt decomposition of a state psi intuitively tells me about the degrees of freedom the state has, or in other words, how close is it to a product state, how many independent parameters I would necessarily need in the Schmidt decomposition to express the state. And intuitively, the Schmidt decomposition is actually tells you how, to what extent, tells you to what extent a state can be simplified. For example, this guy, by the change of bases in the Schmidt form, was just this guy. So it was a pretty simple state. It was a product state. So essentially, what it boils down to is that given a state psi, express it after the Schmidt decomposition, which will actually count the degrees of freedom into a Schmidt form, and then after you have simplified in the Schmidt form, the number of Schmidt coefficients, or the Schmidt number, is going to quantify entanglement or the complexity of the state. And intuitively, what is happening is, we do it all the time, even in classical mechanics or any sort of a problem in physics. We try to see its most simple description. An example will help. So for example, I have a room, and let's say an ant is crawling diagonally across the room, is crawling diagonally across the room. Now, its motion can be expressed, if I have a reference frame, its motion can be expressed in terms of x, y, z. So in a particular reference frame, it has got x, y, and z degrees of freedom. But essentially, if you look at it, you change the axis, you realize that it's really a 1D motion. So essentially, that's exactly what the Schmidt decomposition is doing for us. I take a quantum state and in some basis, it has got a fancy description in terms of some basis. Really, I'm changing my axis, my coordinate system, and reducing it to some sort of a Schmidt form to see essentially how close is it to a product state. And in this definition, my product states are the simplest states, and entangled states, which have a greater than 1 Schmidt number, they're going to be the states which are going to be away from the product states or quantify the complexity of the problem. So Schmidt decomposition in some form, you can say, is a change of quantum system for a quantum state. It tells you about the irreducible. So Schmidt decomposition tells you about the irreducible degrees of freedom of the system. And this is actually very interesting because you can have a quantum circuit. You have, these are the quantum gates. Remember, these were our unitary operators. State going here. Then I have a unitary operator acting on a 4-dimensional Hilbert space, so on and so forth. At each stage of this quantum operation, one can quantify how complex the state is, or what's the Schmidt number. And the way to see that sort of a complexity is to calculate the Schmidt number or so and so, or the entanglement, in other words, of the states. And as we shall see, quantum states which are entangled have superior information processing capabilities. So entangled quantum states have superior advantages, or well, it's the same word, superiority over product states in quantum information processing, quantum computation, quantum metrology, so on and so forth. The idea is to tap into this complexity which is embedded in the Schmidt number and use it to our advantage. So that's going to be our focus. One more essentially good thing is that if you look at it, we've already covered this, but let's say this is my Schmidt decomposition. The number of non-zero lambda i's, or the Schmidt number, is invariant if we apply local unitaries. Well, for example, if I have psi in its Schmidt decomposition, then the same state psi in another basis I change the basis, I am applying each of the vectors of the orthonormal basis on system A by a unitary operator. Well, it's let's say I hit this by a local unitary or just a unitary on system A. This is going to be this particular state, and if you look at it, this is another basis. I can relabel these bases as JA, JB, doesn't really matter, lambda J. If you look at it, nothing happens to the Schmidt number. Schmidt number remains invariant. So when I hit the state, or when the state is acted upon by a local unitary operator, local unitary, I mean a Hamiltonian acting on system A alone, for example, nothing happens to the Schmidt number. So the Schmidt number or the entanglement of a state is invariant under local operations or local unitary. So for example, Alice and Bob can be in Pune and I don't know, Chennai. They can share a state. They have a joint state, which is lambda I B. This is a state shared by Alice and Bob, where Alice has the A system and Bob has B system. Now, Alice can do anything to its system in the sense that it can apply local unitary operations, let's say, local unitary operations. And the state doesn't change. The state changes, but the Schmidt number of the state doesn't change. Lambda is would remain the same. I'll have the same number of non-zero Schmidt elements. I'll just relabel my basis over here. So local unitaries won't change the Schmidt number of a state. That is one of the key properties of the Schmidt number. And so we have actually seen one way to quantify entanglement. Just count the number of non-zero Schmidt coefficients. That's actually going to tell you intuitively how entangled the state is. There are more information theoretic ways other than the Schmidt number to quantify the entanglement, and that's going to be our next focus.